Hey, let's greet each other properly here. Good morning, guys. This is Mr. Aynesworth, and yes, we are in AP Pre-Calc at Grand Oak High School in 2024. All right, we're going to be going over how to use regression and modeling in AP Pre-Calculus. Okay, period two. So I set you guys up the previous day, but if you're absent, obviously you got to talk to your partner here and get everything all set up. Notice that Canvas is on the left-hand side here, and you got your lesson, the data sheets as a PDF in Excel, and you got your homework there as well. And I've got, if you're looking at Canvas on the left side here, I've got all your files that you need. Okay, so you got to get set up first. So if you haven't, you better hustle up and get started. Okay, so let's get started here. This is a video, so no time to goof around. We got a lesson on the left, got a data sheet on the right, so let's read it and let's apply it. So here we go. Got to understand the situation. So while eating out has many fun perks, okay, there are also the associated costs to consider. Is it true that eating out is always more expensive than cooking the same meal at home? Well, if so, this hasn't always been the case. Today we'll look at the ratio, okay, and notice it says ratio, which is a comparison of two different things, of the restaurant to grocery store prices for the same meals over time. Okay, now so when it says the ratio of restaurant to grocery store price, we're talking about this right here. We're talking about the restaurant price compared to the grocery store price, what you have to pay at the grocery store if you made it at home. So this is called a ratio, all right? A comparison of two different things. And what we're going to do is take a look at some ratios. And they have some ratios over here in the data table. Okay, I'm talking about this data table here. It says, look at the data showing the restaurant to grocery store retail price ratio in the year since 1960. Okay, so this right here is important. So we're referencing 1960, so that's at x equals 0 right here. And this is, what do you notice, what do you wonder? Well, you got to look at the data to answer that question. What do you notice and what do you wonder? So first of all, at 1960, that's our initial year, right? So if you're starting at 1960, that means x is 0. 1 year later, that means x equals 1. 2 years later, after 1960, you get the drift. X equals 2, and so on. And you got these restaurant to grocery store retail price ratios. Okay, well let's write that down at one more time. Okay, so this ratio here is the restaurant price divided by the grocery store price. All right, and what do we notice? What do we wonder? Well, if we look here at the ratios, because these are again ratios, okay, the lowest one is 1.4, and then 1.46, 1.48, so they're increasing over time. So that's the first thing I noticed. So it's increasing over time. Okay, so if this is, notice that the smallest one, this is the minimum. That's another thing I noticed, that they're all greater than 1, okay? Which means, tell the person next to you what it means, actually. All right, let's do an interactive video here. Tell the person next to you if the restaurant price to grocery store price, or restaurant to grocery store price ratio is greater than 1, because it starts at 1.42, which is obviously greater than 1. What does that really mean? What does that imply? And if you don't know what I mean, like, what does it imply about the restaurant price compared to the grocery store price? Tell each other what that means. Okay, so that means, okay, here we go. This implies that the restaurant price is greater than the grocery store price. So restaurant price for the same meal, of course, is greater than, let's put this in words, is greater than the grocery store price if you're preparing the same meal. Okay, restaurant price is greater than, so notice that, greater than the grocery store price if you're preparing the same meal. So let's say you're making pasta, right? You're making this chicken parmesan. Now you can make it less at home if you go to the store and buy all the ingredients, make chicken parmesan at home, compared to going out and buying chicken parmesan at, let's say, Carini's or some nice Italian restaurant. It just costs more, my friends, and if you don't believe me, oh, just go and do it and pay the bill, and then you'll know. Instead of your parents paying the bill, you pay the bill and you'll find out. All right, and notice that it's increasing over time. So, in fact, let's dig a little deeper. It says, what do you notice? What do you wonder, right? It says, read the directions. What do you notice? What do you wonder? Well, what else do I notice? Well, let's see here. At 1960, okay, which is the initial year right here, the restaurant to grocery store price is 1.4 basically, or 1.44. Now, if you go all the way down in the data table and you look at 54 years later, so this is x equals 54, at 2014, look at the restaurant to grocery store ratio at 3.842. Now, if you take this number and compare it to the top, and you look at what's going on over time, so what happens, let's write this down, what happens over time? Again, I'm just trying to answer the question here, so I'm looking at the data here. What happens over time? And I apologize for my handwriting here. Let me fix that. What happens over time? You take a look at the two ratios. So let me see, what was it? In 2014, it was 3.842. 2018, 3.842. Now, obviously, look at here, 1960. So 1960 here. Okay, it was 1.442. So if you divide these two, you get the multiplication factor. Like, how many times greater is the ratio in 2018 compared to 1960? Well, all you have to do is divide. So whip out your handy dandy TID4, and let's say here we go. So what happens over time? So let's take 3.842, all right, divided by 1.442, and check it out. It is 2.664 times greater. So 2.6 roughly, 2.66 times greater in 2018. So it's almost tripled. Okay, almost tripled over time. And I'm answering the questions here in problem number 1. Almost tripled over time. All right, so let's go back to the lesson here. Here we go. It says, what do you notice? What do you wonder? Well, I just noticed all these things. I haven't answered the second question yet. What do you wonder? So first of all, what do you notice? Well, first, the ratios are all greater than 1. So first, okay, ratios are all greater than 1. Okay, and that should be obvious. I mean, look at them. It starts at 1.442, guys. Okay, which means the restaurant price is greater than the grocery retail price. Okay, it's more expensive eating out, basically, guys, in like common words. Okay, it's more expensive eating out. Okay, in fact, you can write that down if you want. Okay, secondly, okay, the restaurant prices are increasing over time. So restaurant prices are increasing over time. Because the ratio is increasing, that means the restaurant prices are increasing, okay, over time. That's the second thing that I notice. Well, what do I wonder? Well, we're talking about restaurants, right? Restaurants. Does this include fast food? Because I don't, when I talk about restaurants, I don't think of fast food, okay, guys? I don't know about you guys, but I don't. So what do I wonder? Well, I wonder if fast food is included in this calculation. And I don't know because I didn't come up with this data set. Fast food is included, okay, in this data. There's a lot of other things that you might wonder. So if you wonder something else, go ahead and write that down too. Okay, but when I first looked at this lesson, because I didn't write this lesson, Calcmedic did, that's what I was thinking about. Okay, now instead of using the straplet.com, okay, I decided to use Desmos here, so we're going to skip this. Number 2 here, we're going to use Desmos. That's why I set you guys up using Desmos here. So we're going to go right to number 3. Okay, it says, look at the scatter plot, describe how the restaurant to grocery style price is changing over time, then use Desmos to sketch plot, yada, yada. Okay, so let's go through this here and let's figure out what's going on. All right, so what I'm going to do is let's bring up your data table here, so split screen, and notice that the data is already up there. I set this up with you guys yesterday. Okay, and so we have our lesson on the left and we have our data on the right. And what we want to do is it says, look at the scatter plot, describe how the restaurant to grocery retail price ratio is changing over time, and then sketch the plot here. Okay, so first of all, let's go full screen here since we're on iPads. You guys are on iPads right through here. And then go ahead and click that little button right there. And so we all see the same thing. All right, and let's screenshot this data right through here. And I'm going to increase this a little bit. Yeah, there we go. Okay, so click on, you see this underneath the data table, you see that little magnifying glass with a plus sign? So go ahead and click on that and then expand it. Aha, okay, screenshot. Okay, so do what I'm doing right through here. Okie dokie. Okay, select done, copy and delete, go to your OneNote and do what I'm doing here. So in the free space, which is in between the two documents right here, click on text mode and then press and hold, all right, where the paste icon come up and then paste it in. Look at that, there you go. So I'm gonna bring this in over here, reposition it. If you have a hard time repositioning it, then just go ahead and put it off to the side over your data table, so it doesn't matter if it overlaps a little bit, so don't worry about that. Okay, so I know you guys are working with technology and get used to things, so go ahead and pause the video here if you need to. So, and then when the class is ready, go ahead and press play again, and then that way we can annotate the data table and so on. Okay. So I assume you are ready, so let's get started. So it says, describe how the restaurant grocery to retail price ratio is changing over time, and then sketch the plot. We're using technology, so we didn't have to sketch it. So go ahead and zoom in here. You know what, I'm gonna have to make this a little bit bigger here, so let me do that. Because I have to be able to see, or you have to be able to see this online. So, okay, so here we go. So that's as big as I can make it. All right. So let's annotate a little bit here. So it says, what's happening over time? So when I'm looking at this right through here, this graph right here, I noticed that it's increasing at a steady rate, like right through here, all up until right about maybe right here, and then something changes. Okay, so this is the point in time it changes, and then it just takes off and it goes upward dramatically. So this time went at x equals 0, which is 1960, right through here, 1960, so right about here. All right, which is what year? Let's see here. Let's take a look at this year right here. So this looks like 22, 24, 26. Okay, so 26. So 20 at x equals 26. Now we're talking about years since 1960. Oh, I didn't do that right. I see. So actually, let me redo that. I didn't draw that line correctly here. So right about here. This is the point right here. Let's go down here. And that's about 28. So when x is about 28, which is, let me see, 28, 1960, 88. There we go. So at about 1988, all right, things started to change, and then, all right, it started taking off. Almost looks like, I don't know, either exponentially or maybe quadratically or something like that. I don't know. But I do know that it changes after that. So it's very gradual from for the first, about 28 years. It increases at a constant rate with some fluctuation like right around here in the middle there. However, it increases at a gradual rate, and then all of a sudden something changes at 1988 and it takes off. Okay, you can see this huge increase. We'll talk about that in a minute. Okay, so let's go back here to the lesson here. It says what happens? Describe how the restaurant, grocery, retail price is changing over time. Well, from 1960 to 1988. So here we go. So write small because we can fit in here. So from 1960, which is at x equals 0, all right, to 1988, which is at x equals 28, right there. As we just talked about right here, the price ratio increases at a constant rate. All right, price ratio increases at a fairly constant rate. So what I'm saying is that it's almost linear. Okay? However, things change after that. So after this special time here, this is where the change happens. You know, it takes off. Unless, like, I don't know, something happens in reality. So I don't know what that is, but it takes off. Okay, and then from 1988 onward, so this is the second part. So from 1998, which is at x equals 28, okay, the price ratio increases rapidly. So price ratio, and again, it asks you to respond, right? It says describe. So I'm trying to describe for you guys. Increases, oops, got to spell that right. So increases rapidly. Now, I don't know if it's exponentially, I don't know if it's in the form of quadratic or a cubic, but I do know that it increases rapidly because it goes, the slope of the line is much greater. Okay, you can just tell the slope changes. Okay, that's the first thing I noticed. It says describe what's going on. So I haven't done any serious mathematics, I'm just looking at what's going on. Now, number 4, suppose we wanted to find an equation that would help us model. Okay, so this is the reason why this lesson's called regression and modeling, because you're going to learn that regression analysis is a model that predicts the price at any given point in time. So to model the price ratio based upon the number of years since 1960, so you got to pay attention to the vocabulary here. This is all based upon 1960, which is at x equals 0. And then it says use a least squares regression line that fits the data. Okay, now a least squares regression line is a fancy name for something you learned hopefully back in middle school called the line of best fit. So let's put this in red. So line of best fit, that's what they called it in lower level math. Okay, where you get a set of linear data and you actually draw a line through it, and you call it a line of best fit, which has the form of y equals mx plus b because it's linear. And then later on, we called it the linear regression line. Linear regression line. I actually just taught this in other subjects. Okay, using the slope-intercept form, y equals mx plus b. So when it says least squares regression, we're talking about a linear form of regression line that models the data, that describes the data at any point in time. Okay, and it says calculate the least squares regression line and then write the equation down below. All right, so here we go. So what we need to do is go to Desmos here and get the data set. So I'm going to split screen, and so do this simultaneously with me here because that's what you guys should be doing. Okay, so notice we already have the data set in because I did that with you in class. Okay, if you were absent, then talk to your partner right now because this is important. You can do it in 60 seconds. It's that easy, okay? So we have the data set in here, and the question is like, how do you calculate the linear regression line. So the first thing that we need to do in Desmos, okay, because this is a Desmos technique, not the technique using in number 2 using straplet.com. Okay, I'm not using that software right here. I'm using something very familiar with most people, which is called Desmos. Okay, and what you want to do is type in the least squares regression line, which has in the form, it almost looks like y equals mx plus b, but what you type in is y1 tilde mx1 plus b. That's what you type in. Notice the top of the data table, the title is x1 comma y1. That's why we have the subscripts, because you can use this for multiple sets of data. And if you have 2 sets of data, the second one would be y2 tilde mx2 plus b. Okay, so you can use this as for many data sets as you want. So I'm going to type that in. So here we go. So type in y1. Now to get the tilde, you click on the ABC button on the lower part of the calculator or the keyboard is a tilde symbol. So don't use equal sign because you're going to get an error. Okay, use the tilde. All right, turn the person next to you and say tilde. Okay, which is basically the the Desmos symbol for approximation. Okay, so y1 is approximately equal to mx1. So type in mx1, all right, plus b. So you have to use your keyboard a little bit. And notice that line right there. You know, it doesn't really go through the data that well, right? Because the data is not linear. That's why this model right here, it's called a regression model. Everybody say regression model, okay? It's a linear regression model. It doesn't do a good job at approximating the data. Not very good at all. But it says do it, so we're going to do it. So we're going to write it down, we're going to use it, and then we're going to find a better model because guess what? This is not the best one. Now, if you look here, if you look at the Desmos right now, and click save, by the way, so save your work. Okay, notice the slope is 0.0414. The y-intercept is 1.07348. And all you do is type the values in to your calculator. So you know what? You don't have to do this. I'm just going to do this just for funsies right now. Because you know, I do it right. Okay, so I'm going to copy this. Watch this. I'm going to paste it over here just for funsies. All right. So, let's see where to go. Okay, so there's the data table, but you know, obviously, you guys don't have to do this. Okay, I'm just doing it just because I'm teaching here. Okay, let me get to the lesson right through here. So here's the results. Like I said, you don't have to do this. I'm just bringing this in because I'm teaching the lesson right through here. And all you have to do is just write it down. Okay, so that's not that hard. So you take the slope and the y-intercept and you substitute it in. So our linear regression equation, if you're taking a look at Desmos right through here, is equal to, here we go. So we're going to say y hat. This is the symbol that they use. Everybody say y hat. Okay, this is your prediction line. So y hat, it's a stat symbol, guys, so don't worry about it, is equal to this slope, which is 0.0414481 times x plus b, which is 1.07348. And notice that I wrote all the digits. Okay, so use all the digits. Okay, the reason why for that is because we're trying to be accurate. Okay, now what does this model assume about the price ratio is changing over the years? So what in the world is going on? So first of all, it's linear, right? And we know that a linear function, okay, so this is linear. And what does this linear model assume? Well, everybody knows that linear model assumes a constant rate of change. Okay, so linear model assumes a constant rate of change, okay, of the ratio. All right, you guys know that constant AROC. It's that simple. Okay, that's nothing new. If you're using a linear function to model the data, well, guess what? Everything that you know about a linear function applies. So a linear model assumes that the constant AROC applies. Okay, it changes at the constant rate. Now, do you think this is a good model? Well, I kind of already talked about that already. Okay, so let's go back to Desmos here. So here, uh, I hate it when iPads do this. Let me just close this out. Oh, we should have saved this, you know that? Okay, let me attempt recovery here. So 3 minutes ago. There we go. So save your work, everybody. All right, that's why, you know, saving your work is always good. Look at the data. The line doesn't go through the data that well. This data is curved, okay? It could be better described by either quadratic, or maybe even an exponential function. We have to talk about that. In fact, that's part of the lesson, okay? Because, you know, the data doesn't line up on a long line. It's not linear. It's pretty obvious. Okay, so let's go back to the lesson here. So we're going to say no, data is not linear. It's that simple. Data is not linear. It doesn't get any simpler than that, okay? The growth speeds up over time. Okay, so the question is, if this is not a good model, then the question is like, what is a good model, right? So if a linear regression line doesn't work or doesn't describe the data that well, then what in the world does? Okay, so we'll answer that in a little bit. So first though, before we answer that question, we have to answer number 5. It says the residual plot shows the difference between the actual value and the predicted value. I haven't talked about that yet. So let's go back and actually take a look at what's called the residual plot. Okie dokie. All right, so let's go back to Desmos here. Okay, here we go. And let's see here. We've got that. So notice what I just did right there. Let me go back. Okay, see, look at your Desmos calculator. You see E1 where it says plot, and we see how it's labeled residuals. I'm talking about this right here where it says residuals. We'll talk about what that means. Okay, so that's part of the lesson. So let's click on that. So notice that we have what are called residuals. All right, everybody say residuals. All right, what in the world is a residual? Well, we'll talk about what that means too. So first of all, click save. All right, so save your data. Notice at the top of the screen it says save. Well, let's take a look at a couple points. So let's talk about what residual means. So the first point here is 0,1.442. All right. Now, the actual value or the predicted value is 1.07. That's on your regression model. The regression model is the red line. Okay, it's your linear regression line that gives you your predicted value at any particular point in time. The points in the table are actual values or actual ratios. What the regression model gives you is the predicted value at that particular time, and what the residual value is, and so click on this first point here, is 0,0.36852. It represents the difference between the actual value, which is in purple, all right, and the predicted value, which is on the line, which is in red. Okay, so and that's the definition of residual. Okay, it's actual minus predicted. So I'll tell you what, let's do this. Let's screenshot this and let's bring this in. So screenshot. Now, if you don't know how to screenshot, then talk to your partner right now. Shh. Sorry, that was my wife down there playing with the dogs. Okay, so here we go. So we have what was I saying here? So we got to do that over again because I messed up. So let me do that one more time. So we got the actual value here, the first point. We got the predicted value in red, and then we got the residual here down below, the residuals. Okay, now we want to screenshot this. So use your home button. I think the little home button and the power button all at the same time. Talk to your partner about this. So screenshot. All right, so you can get these coordinates. So notice that I got the coordinates here. All right, screenshot this and let's copy it. So press done and copy it, and let's paste it into our lesson so we can actually annotate it and make sense of this. Okay, so where are we going to paste it? Well, just find a free space. So click on text box. At the very top of your screen, top left, there's a little T, capital T. Press and hold somewhere on the side of your document. I'm using the middle of the two documents. I'm going to paste it in. And I'm going to bring it in and annotate it so we can work with it. So I'm just going to put it on the side. That's close enough. It doesn't have to be, definitely a number 5. It says sketch it in there, but I want to just put it off to the side. I'm going to make it a little bit bigger so you guys can see it here. All right, now let's annotate it. Let's make sense of this is what I say. Okay, switch to red and let's annotate everything in red. So we have our regression equation here. Regression equation. That's y is equal to 0.0414 for a 1 times x plus 1.7348. There's your regression equation, which is here in red. Okay, it's color coordinated here, so it's the line right here. Okay, and then again, I got that by taking the slope and the y-intercept and just writing the equation. Nothing difficult. Then I have this actual value. So let's take a look at the actual value. This is actual value. Just read the table, guys. If you look up here, look at the first point. It's right there. So the actual value is 0,1.442. That's your ratio. Then I got the predicted value here. This is called the predicted value. Now, whenever you use a regression model, it gives you a predicted value, okay? It doesn't come from the data set. It's actually just a prediction tool. Okay, so obviously it's lower than the actual value, right? And that's why the residual is positive, because the residual, so let's right here, this is the residual value. Residual meaning leftover value, and leftover value is found by taking the actual value and subtracting the predicted value to get the residual. So we're going to take this information and let's just take it up here and let's write down our main key idea, a learning target here. So learning, if I can spell here, sorry guys. Okay, so learning target. Okay, so here we go. Predict, or the residual equals the actual minus the predicted value. Okay, so the residual value, and I'll prove this mathematically here in a minute. The residual value is equal to the actual value minus the predicted value. I'm trying to go as slow as I can for you guys. So there's your main key concept of well, one of the main key concepts of the lesson here. So let's prove it mathematically here. So if we calculate the residual value, so it says right here in the computer screen that the residual is 0.36852. So 0.36852, and that should be equal to the actual value, which it says 1.442 minus the predicted value, 1.07348. Let's check that. Let's see if this is actually true. Okay, bring in your handy dandy TI-84. Let's check it. Let's make sense of it, because you guys are going to have to do this. So type it in. So type in 1.442, subtract 1.07348. Okay. Oh, voila. Look at that. You get the right value. Okay. All right. So this is equal. Okay. So there we go. I just proved to you that why the graph is what you give it. So you can pick any actual value and residual and predicted value and then model this. Okay. Now sometimes the predicted value is lower than the actual, so it's an underestimate. So this is called an underestimate. So let's go ahead and write that down. This is because it's lower than the actual, lower than the actual. Okay, you call that an underestimate. Now, I always like to interpret the graphs as I develop it because you won't be able to answer any of the questions unless you actually understand what you're doing. If the predicted value is over the actual value, you have an overestimate. Like right through here in this section, between maybe this point here and this point here, you have an overestimate here. And then before that and after that, we have underestimates. So here we have underestimates between these 2 points, whatever they are, and we'll talk about that here in a minute. We have an overestimate. And then beyond this, like from here on, we have what's called another underestimate. Why? Because the predicted is less than the actual. So take time and mull that over, because these are the answers and some of the thinking that you have to apply when you answer some of the homework questions. Okay. All right. So I'm kind of slowing down right now because we're dealing with a lot of technology right now. We're interpreting right now, which is the most important part of the process. So if you're focused right now, that's a good thing, because this is the essence of the lesson right through here. Okay, now let's go back and take a look at number 5. So a residual plot shows the difference between the actual value and the value predicted by the regression model. Sketch a picture. Okay, so let's see, we already did that. It's over here, so this part's over here. Sketch a picture of the residual plot for the least squares regression line. We did that. Okay, so just remember, let's put this big bold in red. Residual value. Okay, residual value. I'm just writing it down to make a point, is the actual value minus predicted. Okay, key concept. Notice that I've written down in red twice. Okay. Let me see. Did I cover everything so far? So I think so. All right, so let's move on. I want to do a few more, all right, for the first part. I'm going to go all the way till the learning targets, and then I'm going to stop, and that's going to be part 1 of my video. Okay, so number 6, in what years does the regression model give an underestimate? Okay, that means the line, okay, in terms of visual right here, your predicted value, all right, is less than, all right, the actual value. Okay, visually, how do you see that? Okay, visually, the predicted value, which is your line, your regression line. Okay, it has to be under the actual points. Okay, so regression line is under. This is how you do it visually, under the actual points. Okay, so that's how you do it visually. Okay, so let's figure that out. Let's go to the graph and let's figure out in which years. Okay, I don't know, from what to what, from 1960 to what. So here from started 1960. So 1960 to what year? I don't know. Let's go figure this out. All right. So here, so what do we have? So when does it, so let's find the first year. So this is our last point right here. We need that point. So let's go down. Let's switch colors here. What is that? Well, it's 12. It's x equals 12. Holy cow, it's kind of thick. But you got the idea. So let me see. X equals 0 starts at 1960. Well, then 12 years later, that's 1972. Okay, how about the next one here? So here, let's just pick this one here and let's go straight down. What year is that? That's 24. That's 4 years past 44. That's x equals 44. That's close enough. So let me see, 44 and 60, that's 2004. Okay, so I didn't say it. Did I say that right? Let me see. X is 12. Oh, yeah. Okay, so 40, 45. So that's 44, but you notice the next point here is at 45. So this next point here, this one, and I'm looking at the one here right next to it. If you go straight down, that's the next year. It's in between 44 and 46. So I think that sounds like 45. So starting at 45 here, 45 and 60, that's, well, that sounds like 2005, right? So 2005. Okay, so 2005 on, okay, the actual is greater than predicted. So again, this is actual. Okay, the red line, this is the predicted value here. When you're on the regression line, this predicted value. So whenever the actual is greater than predicted, it's an overestimate. Underestimate. Come on, Aynesworth is right here. So when the predicted value is less than the actual, it's an under. When the predicted value is greater than the actual, it's an overestimate. And when the predicted value is less than the actual value, which it is between 0 and 12, or between 1960 and 1972, like in this right here, we have an underestimate. Okay, so let's take these answers and let's bring them over. Okay, so what did I just say? So from 1960 to 1972, that's our first interval. So from 1960 to 1972, from x equals 0 to x equals 12. All right, and, okay, we have another interval. So let's go back to the graph here. So when you're beyond 44 years, so 2004. So when you're at 2025 on, okay, to infinity, all right, you have an underestimate. Okay, so let's write that out. So from 2005 on, which is at x equals 45 years on, okay, to infinity, you have an underestimate. Okay. All right, in which years does the regression model give you an overestimate? Okay, so if you have an overestimate, that means the line is above your points. So that's in the middle. Okay, and that's in the middle of this. So when the regression line is above the points, okay, you have an overestimate, and that's between 1972 and 2005. Okay, so let's write that out. So from 1972 to 2005, which means that you're dealing with it as x, it's from x equals 12 to x equals 45, you have an overestimate. Okay, so those are the two basic questions. All right, what should you expect the residual plot to look like if the regression model is a good fit? Okay, so good fit for the data. Well, to be honest with you guys, I don't know how you would know this without, some experience in stats. All right, but this line is obviously not a good fit for the data. So when you see the residual plot, so let's go back to the graph here. And this in purple, let's put it in purple because it's in purple. So this is your residual plot. That's what it's called. It's called a residual plot. When the residual plot has a pattern, like it does in this case, it looks like a parabola because it's curved like a parabola. All right, it indicates that you don't have a good model. Okay, it should look random. Like if the regression line actually went through the points, some should be above and some should be below, not like this. Okay, so if the residual plot shows a pattern, okay, so it shows, and this is a parabolic pattern by the way, because it kind of looks like this. Okay, look at that. So if the residual plot shows a pattern, which it does, it's parabolic. All right, say that to the person next to you. Say parabolic. All right, it indicates that the regression model is bad. So regression model is bad. So what that means, you should switch models. I'm writing down the logic here, guys. You should switch models. Okay, so the question is like, what models should you switch to? And that's where we're going to right now. So we're going to go to explore that. So let's do a few more things. All right, so but before we do, let's write down the answer to number 8. So what should you expect? Okay, and we should look for a random pattern. Okay, so the residual plot, let's write this down. Residual plot should be random, no patterns. Getting all crazy with my handwriting here. Should be random. All right, no patterns. Really, really important. Okay, it should be like, when you look at the residual plot, you should be points all over the place. All right, and if you see that, that's a good thing. All right, if you see a pattern like we did over here, like it is in the shape of a parabola or something nice shape function here, that's a bad indication. You have a bad model and you got to switch. Okay, number 9, and this is the last one. Well, number 9 and 10. Okay, and then we'll do part 2 later. Okay, perhaps a linear model is not the right fit. Well, duh. Okay, I talked about that. Okay, so the linear model is a bad model. Okay, why? Because the data is not linear. Okay, that's the reason why. Data is not linear. I'm going to say it down. Say it again, okay? Okay, but we learned how you can also tell. We learned that if you look at the residual plot, if you see a pattern, it also indicates that you have a bad model and you got to switch models. So under the calculate under regression model, okay, this is for the app that we're not using. You can see what quadratic or exponential model looks like. Okay, so I'm going to show you how to do it in Desmos here. Okay, describe what the quadratic model indicates about how the restaurant to grocery ratio is changing over time. So let's take a look at the quadratic model here, and then we're going to write the equation of the quadratic model. So let's write down how you write it in Desmos. So I don't know what the other program does, but this one here, the quadratic model looks like this. So y1 tilde, okay, ax1 squared plus bx1, okay, plus c. That's in the quadratic form that you saw, in Algebra 1 and Algebra 2. So what we need to do is enter that in and see what it looks like. Okay, so let's go back and let's split screen. Let's bring back Desmos here. And let's type it in. So here we go. So y1 tilde now. All right, mx1 squared. Now you got to square that bad boy because it's got to be a quadratic model, right? It's got to be squared parabola that you guys are familiar with here. Plus bx1. So bx1. All right, plus c. All right, so a little tricky. Go ahead and enter that in. And let's go full screen and let's take a look at this because it's kind of hard to see it when you're in 50/50 mode, okay? So notice I saved it before I went to full screen because this always happens on an iPad and I don't know why. So you're gonna have to reopen your graph, okay, and there it is. Okay, so always save your data before you go full screen because of what just happened to me. So notice that the quadratic function, the parabola here, goes through the data a lot better. In fact, once you get past the 12, 14 years, and look at it describes the data really well. Look at that, a lot of points. It goes through a lot of points. It's a much, much better model. Okay, so just keep that in mind. So that's kind of cool. All right, and then, how does that compare to an exponential model? So let's go back to the lesson real quick, and I'm going to go ahead and, actually, no, I'm going to import this in right now. So let's go back to Desmos. Let's import this in so we can see it. So there's our quadratic model right there. And we'll get the equation here in a minute. So let's screenshot this. All right, bring it in, copy it, go back to OneNote and paste it in. See, there's a lot of tech in this lesson, so just click on text box, press and hold, paste it in, you're good to go. That's the fastest way you can do it. Okay, so there's your quadratic model. All right, and let's annotate it. So when you're writing the quadratic model, you take your values here. Whoa, why'd I do mx plus b? You know what? I don't know. I can't believe I did that. Usually I use A, B, and C. I don't know why I put M there, but that's okay. So this value here, they give you the M value, they give you B value, and they give you the C value. Okay, so now let's just write it. So your quadratic model looks like 0.00109,738 times x squared minus 0.0178103 times x plus your C value, which is 1.590,693. So there's your function right there. Holy cow. Okay, so we have our quadratic model. So let's bring that over here and let's write that down. So my function looks like y is equal to, again, 0.0010973. I'm just reading my notes here, x squared, right? Minus now. So minus 0.078103 times x plus 1.59693. There's your quadratic model. And it does a really good job. This is a good model. So let's go back to our graph and make a note of that. This is a good model because it goes through the data points. So write some notes to yourself. Visually, it's really easy to see if the model's good. You can even see, look at the r squared value right here. Okay, this right here, when this is close to 1, okay, this is close to 1 if you look at it right here, and that tells you that it's a really good model, okay? Very good model. People that have taken stats know about that really well, okay? Always look at the R value with correlation coefficient or your R squared value when you're dealing with degrees that are greater than 1. Okay, and 0.99 is very close to 1 if you just round it. Okay, that tells you have a very good model. It goes through the data points, as I just said earlier. Okay, so but now it says describe what exponential model indicates, okay, and as it changes over time. So I'm going to focus in on the equation. So I'm going to, just for the sake of this lesson here, I'm going to skip A and D and go, well, actually A and C. Sorry, so A and C, I'm going to go right to the equations and get right into it. So let's talk about the equation for the regression model. Now the regression model, okay, looks like y1 tilde Okay, a times b to the x1 power. That's what you type in. So let's go back to Desmos and do that. And then let's get the regression model and we'll see which one's better. Is the quadratic better than the regression or exponential function? I don't know. All you have to do is type it in and compare. So here we go. So y1 tilde, all right, a times b. So a times, okay, it takes a second, but just type it in exactly how you see it. Now you got to raise it to the power of x1. Okay, and then go full screen, save it, go full screen. Always save it before you go full screen. Oh, wow, it did it fine. So look at that there. So now turn off the line, turn off, don't delete, okay? Just turn off the colors. So you're only looking at the exponential model, okay? Now, when you do this right here, click on log mode, just so you can see the R values and the R square values and the residual plots here. So if you look at the residual plot on this one, so let's see here. Turn off the previous one. So, and you're only looking at this one here. So this one's not very good either because it has that curved parabolic shape on the residuals. And notice that it doesn't go through the data points very well. It's above, below. It's above first up until like x equals 12, and then it's below. It's almost as bad as the line. Okay, so this one here is not very good at all. Okay, so let's screenshot this bad boy. Let's bring this in. So copy it and let's paste it in so we can see things side by side. So let's paste it in. Click on text box, paste it in side by side, and you'll have two good graphs to compare your lesson with here. Look at this. Okay, look at that. All right, and you could tell that the one on the left with the parabola, okay, the parabola is a good model, so the line's bad. This is linear. Okay, that's a bad model. Okay, the exponential on the right, this one here, this is bad too. Okay, we're not good. Okay, so the exponential model, okay, not good for a variety of reasons. Okay, first of all, it doesn't go through the data. That's explanation number one. Notice the residual plot down here in green. This is the residual plot here. Okay, notice that it has a pattern. Okay, so because it has a pattern, it's obviously parabolic pattern, parabolic pattern. That tells you that it's no good. That's how you tell. You look at the residual plot. If it has a pattern, the model's not good. Visually speaking, if the model doesn't go through the points, not good. But the residual backs it up. Okay, so always look at the residual. In fact, let me write that down. So always look at the residual plot, which is right in front of you. It's right here. Okay, and if it has a pattern, it's no good. So a lot of this. Now, again, if you're having a hard time with the technology, then guess what? You can always listen to this at home. It's a video, right? And you have access it anywhere in the world, okay? And if you don't get it, then go listen to it again and go slow, go at your own pace, and then strive to learn, okay? Because I know that when someone's going over something technical, it's tough sometimes. But hey, I can't do it any better than this, and this is exactly what I'd do in class, okay, if I was with you guys. You're lucky you have a video because then you can pause and play and rewind. Okay, how about that? Okay, so let's write down the function here. So our exponential model, what does that look like? Y is equal to, I don't know, I have to go grab the values. So here you take these values, all right, and you substitute them in your function. So 1.28, so let me see. So y is equal to 1.28539 times b, 1.01821 raised to the x power. There's your exponential model. All right. So let's write that down. So 1.285 1.28539 times x to the 1.01821. Excuse me, I didn't write that in. 1 point, I forgot it. So 1.01821. 1.01821 raised to the x power. Okay, so now we have our two models. We have the quadratic model, okay, right here. And then we have the exponential model down below. And then looking at the residual plots, and I already talked about this, which function do you think is better? Okay, and so this one I said was no good because the residual plot had a pattern. Residual plot had a pattern. Okay, and this one right here, if you look at the quadratic model, where to go? I don't have the residual plot shown here in the screenshot, but look at the residual model. The correlation coefficient is 0.99 and it's very close to 1, very good model. And if I was looking at the residual plot, we would notice something, no pattern. It was good. So this model here, this is your best model, the quadratic model. So quadratic model is the best. All right, using your chosen model, predict the retail price ratio, all right, for 2023. So we're going from 1960 to 2023. So how many years passed? Let's see here. So we just need to subtract, right? Okay, so that's 63 years passed. So x equals 63. So we substitute our model. So we're going to take this model here, our best model, and we're going to use it down here. So y is equal to 0.0010973 times 63 squared minus 0.0781303 times 63 plus 1.59693, and we're going to figure this out. Okay, so what is this approximately? So bring up your calculator, and this is the last thing we're going to do, you guys, and then I'll do the rest in the next video. Okay, part 2. All right, so we just type it in. So 0.001973, all right, times 63 squared, all right, minus 0.078103 times 63 plus 1.59693. Hopefully I typed that in correctly. So here we go. And I get about 4.5. Okay, because I used a lot of digits. Okay, so y is approximately 4.5 in this right here. So, excuse me, 4.5. Yeah, that's close enough. Okay, and then and this is 63 years after. So this is your ratio right here. This would be the restaurant ratio. So restaurant to grocery ratio. Okay, after 63 years. Okay, we're talking about in the year 2023. All right, 4.5 times greater. That's what this means. So restaurant prices, this is what, if you had to interpret this, is it. So restaurant prices would be 4.5 times greater, all right, than 1960. Wow, guys, that's called inflation. Okay, and there we go. Now, in the second part of the video, this would be part 2 here. I'm going to stop the video here because it's long enough. All right, here I'll talk about the learning targets and I'll apply everything, and then we'll go into the homework. Okay, and this is what you guys do at home. Okay, because you got to do some homework, right? All right, so I know you can't be with me, so I did this for you guys. Make yourself proud, do the right thing, study well, do your homework, use my resources effectively, and of course, this is a video, right? And as such, you can use it effectively. So if you need to go listen to any part of this on your own at your own time, my advice is to pause, play, and rewind at your speed. And then you obviously get the lesson. Because I know it's tough sometimes, especially when you're trying to learn mathematics and use technology at the same time. All right, so go at home, do your best, and I'll see you guys back when I get back next week. Guys, take care. Bye-bye.